So our next panel is organized by Matt Cook and Vincent Bohosian, and its topic will be neural networks and AI. So Santosh Venkatesh, Jigao, and Dan Wilhelm.
So Shuki, I have a little gift for you. Something that I think is maybe something that you would not expect to get. Here, try it. A new binary addition algorithm. How could this exist? Binary addition is binary addition, right? There's only one answer. You kind of need to add the digits. What are you going to do? Okay, so here we go. Where does this come from? You remember in my thesis, this is a snapshot from my thesis. You remember these zipper networks, right? There are these little zippers everywhere. Yeah. They can zip and unzip and go around. And then I had this little, algebra of operations that you could do. Okay, and then so now I'm working in an AI department. So in AI, what would we like to do? We would like to make a machine that you just expose it to raw data in the world, and somehow it develops an understanding. It's impossible, right? Except our brain is such a machine, right? You just expose it to raw data, it develops an understanding. So we try to model this. And then I recently realized that these zipper networks, which were in the thesis, even though they had no purpose whatsoever, they weren't used for anything. I just thought they were nice. And now, 20 years later, finally, for the first time, they have a use. Okay, so I'll tell you the algorithm. I won't explain the whole, it would take an hour to explain how you get to this algorithm. But by trying to just develop a machine where you turn the crank on the real world and develop an understanding, we turned the crank on a one-dimensional real world of addition problems, and we came to this understanding. A new algorithm. I call it the dot copy fill algorithm. So did you watch those Zorro movies? Where Zorro always puts the Z, zip, zoom, zoom. Okay, that's how the algorithm works, okay? So it has 3 stages. It sounds super complicated, but this is much simpler than the regular one, right? Each stage is trivial, and the stages go zip, 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 just like Zorro. Okay, so the first one is the dot stage, as you might guess. What do you do? Every place where the digits match, you put a dot. You remember, we would have meetings every week. I would come in and I would show you what I'd been thinking about. One time you just started laughing because you said every time I draw a diagram, it's the same. It doesn't matter what we're talking about. I just start drawing a lot of dots on the board. So of course that's how this starts. Okay, so we put dots everywhere the digits match. You have to admit this is a trivial stage, right? Okay, and then we're done with the first stage. You could even imagine all the trailing zeros, all the leading zeros, infinite number of dots. We don't have time to put an infinite number of dots. Okay, so the next stage, the copy stage. Now we're going backwards. We just copy the bits. The reason we put dots is these are the positions we look at, right? So we're going to go backwards. Okay, so we just fill in under each dot. We copy the bit from the previous position, right? There were 1s, so we put a 1, right? There were 0s, so we put a 0 under the next dot. That one has 1s above it, so we put 1 in the next position, and so on. Right? And then the 1s above this dot, where do they go? Of course, to the next position. Okay, and then again, we can fill in the infinite zeros, but no time for that. Okay, finally, you have to admit that stage was also trivial, copying, trivial. Okay, now fill, right? We have all these gaps. We have some digits of the answer, but they have all these gaps. So how do we fill in the gap? We fill with what? We look at the leading digit, and we fill with the opposite digit. Leading 1, we fill with zeros. Leading 0, we fill with 1s. 0, fill with 1s. 1 fill with zeros, 1 fill with zeros, 0 fill with 1s, and we're done. That's the sum. I hope you haven't seen this before. For me, it was new.
Thank you. I love this present. By the way, if you look at Leibniz writing from 300 years ago, the way he symbolized the places of care is by having dots.
Oh, dots.
So I think you are the new Leibniz. because you are using dots for addition. But I think I'm sure it's a different algorithm.
Yeah. Okay. Great.
Switch.
Yeah. Okay. And unlike the normal algorithm, with this algorithm, it's obvious that addition is symmetric in zeros and ones. We're used to the normal algorithm; it's not at all obvious. It's symmetric in those.
All right. Okay, continue.
Okay. Yes. Please. Yes.
Thank you for inviting me here. It's been 13 years since I came to Caltech, and it's paradise. Every time I come back, I just feel happy. And I couldn't miss. Shuki is one of my oldest friends, and he and Yasser and I shared a room in the basement of Steel. We joined Caltech together, both had the same advisor, and ended up doing things which our advisor didn't do. That was Caltech in a nutshell. And one of the nice things about talking near the end of a session is because everybody has said the stuff that you were going to say anyway. So you don't have to do anything about it. Incidentally, I never communicated my accent, whatever it is, to Shuki, ever. Okay, that hasn't happened either. But I do remember my daughter, one of my daughters came to Caltech, and she took Shuki's class on logic and information, and it was by far her favorite class here at Caltech. She's a symplectic geometer. And she would tell me, Dad, you can't believe what we heard today. Okay, great, this is wonderful. I'd say, what do you do in math? No, forget the math. This was neat. This was fun. By the way, she also had particular kudos because she thought of Shuki as Uncle Shuki and Yasser as Uncle Yasser. And I can't tell you how much kudos she got from her classmates. He called them Uncle Shuki and Uncle Yasser. I mean, good grief. But I was supposed to talk a little bit about AI. I am not going to try to trump you with an algorithm. You're saturated, so we're not going to do this, okay? No more dots and dashes. By the way, a dot was also the ancient zero by an Indian mathematician around 200 AD. Okay, where the first time a zero was discovered. It was the wall of a temple in Orissa. So, a Leibniz and the discovery of zero, you're in great shape, Matt. Okay. Back to AI. 40 years ago, almost to this day, the first workshop spawned by, you might have heard of this guy, John J. Hopfield, neural networks and physical systems with emergent collective computational abilities, 1982 in PNAS. That paper came out. And we were new at Caltech at that time. Yasser and I had joined in 1981. And we were excited. This was fun. This was a bubbling, vibrant place. And the first workshop spawned in that surge of neural networks was in 1985. It was in Santa Barbara. And the banquet before the workshop kicked off in earnest was a lecture by John Hopfield. It was called The Past is Prologue. There was also a guy named Bernie Woodrow from Stanford, and I'll come back to Stanford at the very end just a bit, okay, who was there during that day. And the whole idea that Hopfield was talking about is, yes, this is exciting, this is new. In those days, that workshop was spawned between Caltech and Bell Labs. And that became, after a sojourn through Caltech, it became the annual Snowbird workshop in computational systems a few years before the first NIPS started, for which Yasser was the general chairman. Okay, so there's a long connection between these neural network bears and Caltech. But the past is prologue, and what Hopfield was talking about was there are surges in the development of an area. And that was just the current surge. I remember Carver offering a course with John Hopfield and Feynman on the molecular basis of computation at that time. That was quite remarkable. Okay. Surges. And with each surge, the surge comes to a halt in the natural scheme of things because we hit insuperable technical problems, mathematical issues we can't solve, the technology wasn't there. As Yasser pointed out in his Watson lecture a couple of years ago, the luck wasn't there. We're in the middle of the latest surge in deep learning, dating about a decade, 12 years or so. But there is a fundamental difference, in my view, between this surge and the ones that preceded it. And this is a philosophical difference. And to put that in context, let me take a couple of minutes to just set the stage for you. For me, AI, for our purposes, is neural networks. I'm not talking about expert systems. And if you talk about neural networks, you go back to the beginning, the paper by Warren McCulloch and Walter Pitts, which you've seen referred to. A logical calculus of the ideas immanent in neural activity, 1943. If you haven't read that paper, it's remarkable. We don't read original papers anymore. Incidentally, another paper which is referred to, which you've seen on screen today, Lulu, I think, mentioned it, Eric did, a paper called The Harmonic Analysis of Polynomial Threshold Functions, which is published by Siam in 1990 by a certain Shuki Bruck. One of the most elegant, beautiful, fundamental papers written. If you haven't read it, of all the papers, pick that one. Take a look at it. It's remarkable. But what are these surges? McCulloch and Pitts, 1943. 6 years later, through biology, D.O. Hebb published The Organization of Behavior, 1949, in which appeared the philosophical underpinnings of a learning algorithm that biology might anticipate. And 7 years later, Frank Rosenblatt at Cornell came out with the perceptron, with an algorithm and a learning guarantee. That surge died. True practitioners kept on, but a new surge, 1982, with John Hopfield. And there was excitement on campus. You should read Yasser's paper on computation from that time. Shuki's paper, 1990. Brilliant, fundamental, and what did it do? It abstracted out complex ideas and brought forth simple ideas at the heart of that complexity. George Poley would say this: when you're faced with a complex problem, don't attack it. Poley would say, what is the simplest version of the problem you don't understand? Solve that. Shuki understood that very, very well, and one reason I was drawn to Shuki the first time I met him. It was brilliant. That surge, again, you articulate fundamental principles, and then you understand more complex behavior. This was at the heart of, actually, when you think about it, much of engineering design. This surge in neural networks is different. It's born by luck, timing, technology, GPUs, all that stuff. But also, this is the first surge which is driven primarily by empirical results, by data. The fundamentals are lagging a long way behind. So I'll ask you one question. What problems are neural networks well suited for? We don't have a good answer because we don't have an understanding yet of what goes on inside that black box. So one thing I'd ask is, as we now try to catch up with where the ChatGPTs and the Geminis are leading us, an understanding of the fundamentals will help produce a more verifiable, quantifiable future. A small proscript, that same workshop in Santa Barbara, the precursor to Snowbird, the first technical lecture, the next day was by Bob McLeese, and the luminary right here at Caltech. And Bob, Ed Posner, Gene Rodimich, and I had written the first technical paper after Hopfield's paper. It was called The Capacity of the Hopfield Associative Memory. Carver might remember it. But the first paper was by Bob McLeese. And unfortunately, the organizers had cut out the last word of the title of the paper. And the title read, The Capacity of Hopfield. John was sitting in the front row. Bob gets up, looks at the audience, and he had a wonderful, droll sense of humor. He gets up and says, our paper was on the capacity of the Hopfield associative memory, but I understand the organizers wanted to talk about the capacity of John Hopfield. On this subject, I'm sorry to say, we have no results whatsoever. And he sat down. Thank you.
All right. I'm going to use... Okay. All right. So first, it's a great pleasure and honor to be here and to be included in this panel. I was here at Caltech from 2004 to 2005 as one of the first batch of CMI postdoc. I checked with Leonard. So it was a great year. It was, again, it was also part of because of the specific, the nice thing about Caltech that make the year to be really wonderful. So I had the opportunity to work with Leonard and Michael Lamberg on some geometric problems, also work with Shuki and Andrew on some networking problems. I think also Michelle invited me to her group meeting. I enjoyed a lot. But one thing that I probably didn't realize back then, but it becomes very clear to me right now, like what I truly learned from that year, it was the experience of a truly interdisciplinary environment, that people talk to each other and are genuinely interested in each other's problems and work on something that are very novel and very different from other work. So when I was asked to talk about neural network and AI and how this connects to the work that we have done in the past, it was not an easy question. But I thought about it, and I want to say what was really the one thing that we did back then and carried over with me for later of my work. It was this topic of geometry plus network. So I prepared some slides, but not really on the work we did back then. So back then, we worked on problems such as network localization, and it was a problem of you have a bunch of vertices, and you have some measurements of these pairwise distances or maybe angle information, and you want to find out where they are. So we call that network localization. And now with the neural network and machine learning, it's almost the same problem, that we have similarities of some objects, and we call that representation learning. So I want to use this example to say it's actually lots of things that similar ideas that gets used and applied in different problems and different fields. And so what I want to show, maybe using the slides, nothing technical, I don't want to explain anything, but more of some of the samples of the work that I did after I left Caltech, that again has geometry and intersection with networking problems. So just want to show that this is, again, something that continues to be fascinating to me. And so in fact, just one thing, skipping some slides. So that is geometry. We talk about curvature. But we could also talk about curvature in network setting. So let me just show some examples. So here is internet autonomous network, and we can also talk about curvature of edges in this graph. And we can use that in maybe a number of applications, such as community detection, by using what's called curvature flow, a notion that is carried over from continuous differential geometry setting, but again to the discrete setting. And to do detection of a karate club network, some Facebook network, that we can sort out these different communities automatically by using this curvature evolution. And again, Another example which is more recent is our work on using computational topology for analysis in machine learning, in particular in graph learning problems. Again, all of these basically have the elements of some geometry and also plus a networking application. This is a theme that we started back 20 years ago, but continue to find interesting new applications right now. Yeah, I'm gonna pause here, and if anyone has questions or asks about these pictures, I'm happy to answer them more. Yeah, all right, and thank you, Shuki.
Hey everyone, I'm Dan Wilhelm. I was a PhD student in Shuki's lab. I also was head TA for IST4. And I've done quite a lot of teaching since then, and I have Shuki to thank for knowing how to do this. I'll tell you the secret. When do you use 100% Comic Sans? You use it when you understand that something is exciting, but your audience doesn't yet. I also learned from Shuki, when giving a talk, you should always start with a joke. I did computation and neural systems at Caltech, joining Shuki's lab. I feel like what we really tried to do was understand models of computation. And I've been fortunate enough at Caltech to get some experience with everything down there at the bottom. And Lulu mentioned some of the collaborative work we did. We took a switch, we made it probabilistic, and we tried to answer, what can this compute? And we tried to build circuits of switches that were optimal in some sense, that computed probability distributions. And I feel like this was a really good preparation for now, because back in 2011, when I was a grad student, the question was, can we compute language? It was an unknown. Many people thought that language was a unique thing to the human brain. But nowadays, the question has turned to more so be, well, we have these large language models like ChatGPT that can maybe in some sense compute language. And the question, as was just mentioned here, is what is that model of computation? If you have a complex system, as an engineer, you know that there must be some underlying principle. And so I think a challenge now, some people would say a challenge that has to be answered quickly, is to understand what that principle is that LLMs might use behind the scenes. So recently I've gotten into a new field, subfield called mechanistic interpretability. I think it's a perfect combination of neuroscience, which I studied in CNS here, and my experience in Shuki's lab. It actually tries to use techniques from neuroscience, patching, probing, a little callback from Christoph there, of, can we interpret what a single neuron does? Is there a Jennifer Aniston neuron? But let's try to use these techniques to study LLMs. So I've been working in this area for a bit. Last year, I contributed a paper to the first MECINTERP workshop at ICML, and currently in the final stages of possibly getting a pretty good-sized grant to continue work in this direction. So thank you, Shuki.
Hi. So
Let's see, I started at Caltech in the fall of 1993. So before Shuki had arrived, actually, I was a grad student, and there was no more building at the time. I was also in the basement of steel. And in the spring of '94, I was taking Yasser's class in information theory, and Shuki was giving a lecture on threshold circuits and his research. I was really interested in neural networks, but I was also very much into math and proofs and theorems. So his research was very interesting to me, and his personality, of course, very captivating. And so I was very happy the following year that I was able to join his lab as a PhD student. My research was focused on the weights of neural networks and how limiting the weights in some way would affect the power of the neural network. But also I was involved in many of the projects in the Paradise Lab with the other students. So, and also in Reinfinity, the Shuki startup. So that was very rewarding, very fun times. I'm very grateful for the opportunity to work on all these different topics. I think it helped me a lot in the following years to problem solve, and I worked on many different companies and started my own company. Did some augmented reality, virtual reality, worked with celebrities in Hollywood somehow. And now I'm back to doing neural networks. Also working with the weights of neural networks in the context of training and fine-tuning generative AI for visual effects. So I think we have 3 minutes left for questions. Thank you, Shuki. Thank you, guys.
So if anyone has questions for the panel, don't be shy. While we're getting started, I have one question I'm curious about. So I would always sit in Shuki's group meetings, which I loved, and I always try to make my group meetings, I form them on that model. And, but it was a little bit of a strange thing because everybody else was doing coding theory. And then I was doing, I don't know, nobody knew what I was doing. I didn't know what I was doing. So, so I always felt like a bit of an outlier. And, you know, and so my question for people on this panel for neural networks and AI is how do you feel about this topic being connected to the other topics that Shuki has worked on? Or do you think it's a separate topic and that Shuki has multiple interests? Or how, if you have some idea how you see it.
I mean, I already explained it a bit from my perspective, but I think everything Shuki does is from first principles. And I think that's something that's, that we sort of need to look at closely at the latest generation of neural nets.
Perhaps I could chime in as well. I don't see necessarily that these topics are directly, linearly connected. On the other hand, this is an amazingly curious individual. He's interested in all kinds of things, and they don't have to be connected intellectually. But there is, yes, of course, a fundamental underlying bedrock principle, which is first principles. And this comes down to a culture which all of us here are so familiar with, the idea of the fundamentals being important. You know, of course, Shuki was the first to discover this, but he's one of the modern exponents of this idea. You know, if we go back to George Follier, he talks very eloquently about this. If you want to go back to the 13th century, to a guy named William of Ockham, the Kentish village of Ockham, a Franciscan monk, you know, he has collected works on the Quodlibet Beta, and here you'll find phrases like this: pluralitas non est ponenda sine necessitate. It is not wise to embrace complexity without necessity. At the heart of all these things that Shuki has looked at is not, I think, necessarily a connected intellectual subject leading one into the other. It's basic principle about here are simple ways about thinking about complicated things. And if you understand simple things, then that opens the door to understanding complexity. When you think about modern AI, we have reversed the process. We've got these very complex things, and we haven't found good, simple abstractions for them yet, which explain what they are. And just to give you a quick illustration, we talk about deep learning. What is deep? In 1995, I ran a workshop at NIPS when I was still interested in neural networks. I don't understand complicated things. So, following Shuki, I want to simplify it. So I don't understand what deep networks are doing. I have no idea. So I asked in the workshop, put together a bunch of brilliant people. I think Shuki might have been there. I know that Stephen Judd was there, Yasser was there. But what does depth 3 give you that depth 2 does not? And at the end of the day, we had formidable intellectual power there. And we got absolutely nowhere. And that's what I mean by fundamental questions. If you understand that, then perhaps it opens the door to something else.
I want to just add, maybe, for the year that I was here, also with Shuki's group meeting, again, lots of people talk about coding theory and other things. And I don't think I have ever published or have done anything for coding theory per se, but I think what I learned from the group meeting, from the other problems that people care about, clearly helped me to look at lots of things in different perspective. So again, fundamentally, a lot of these elements are connected, and they may look like they're for different applications, but again, they're helpful. They were helpful for my case. Yeah.
Yes, these comments remind me that I was working on a model of how the brain works, and Shuki said, "Oh, you need to read this unpublished thesis of this guy from 1920. I don't know how he knows these things. But he was exactly right. Charles has stood up. I think this means we're out of time. We have a question. Yes?
So as LLMs are getting more and more capable, everybody's talking about and celebrating how LLMs are great tools for research and how they're going to accelerate research. I often think about there's a ton of people celebrating the positive aspects of LLMs, but what are the downsides? As researchers at the cutting edge of LLMs, what keeps you guys awake at night? What questions do you grapple with on the downsides?
Well, I think that LLMs are known to make mistakes. So you can argue, well, if it's a proof, you can always verify it. So the LLM comes up with a new proof that no one found before. You verify it, it's correct, that's great. I don't know how much that has happened so far, maybe at Google. But yeah, I think there are cases where the LLMs are known to hallucinate, to make mistakes. So definitely the results need to be checked, I think, if you want to use them for something like research and math and things like that.
I agree. Maybe just a comment. I feel like although this AI and LLM and all these generative models are wonderful, but there are also potential issues and kind of dark side of it. That is, it's now so easy to generate new content, fake content, and like, I think something maybe we will worry, or maybe we should worry right now, is how much of the information space is already polluted by all of this generated content, and if this iteration will cause big problem down the road. I don't think we fully understand the scope and consequence of this.
Perhaps I could add one more word in this. Look, for gloomy views of this, you can read Jeff Hinton's views on the potential for things to go badly, to use a Scottish word, agly, for things to just go belly up. Yes, there's a huge potential because we don't understand at heart what is the foundational driving mechanism. But if you want to see a positive view of this, or relatively positive, listen to Yasser's Watson lecture from 2 years ago, where he takes a slightly more positive spin on this. Yeah, there are issues. I can tell you, it's not just malicious actors. About 3 weeks ago, a theoretical computer scientist who I know well, who is a mathematician and a computer scientist, reached out to me about a question in probability, presumably reasoning that because I've written a book on probability, I know something about the subject. And he said, I asked ChatGPT this question, and it gave me this answer. And it looked elegant, beautiful, closed form. I took a look at it, and it was a question on random walks and grids, and okay. And I reached out and said, actually, this particular problem does not have a simple closed form answer. There is a differential equation, which actually goes back to Leibniz, which can be put down, but there's no closed form for this. All right, so he goes back. Now, this is a highly regarded computer scientist, and he starts probing ChatGPT about, look, you give me this answer. It took him, he told me, about 2 hours of increasingly specific probing before ChatGPT confessed that it had made it up. Now, this is dangerous, because now we're talking about not a casual user, you're talking about an expert. An expert provided with an answer which he could not verify, which turned out to be fallacious. And at the heart is because we don't fully understand the guiding principles behind this. So let me ask you this. Look, as a mathematician, I look for symmetries, I look for simplicities. I don't understand complicated things. One of our tools is asymptotics. The calculus is based upon going to infinity. Why? Because finiteness is a messy, real-life problem which creates edge effects we don't understand. You go to the infinities. We can talk about asymptotics in the size of input. Have you thought about asymptotics in the depth of a network? The idea, create symmetries. Not that it's real. No real network has infinite depth. Fukushima's neocognitron from 79 had 7 layers. No matter. But to understand what these things do, we need guiding principles. And to date, we don't seem to have them. And that would be a good place for folks in this room to actually make progress. I don't know how easy it is at Google or Meta or OpenAI to make progress in fundamental issues. The economic incentive there drives a very great deal. But at a place like Caltech, at a place like Penn where I work, yeah, perhaps. But this is where there's an opportunity in academics. I'm sorry, I keep proselytizing, and maybe I should just stop.